Okay, we're just going to finish up exercises D and E from day 24 because we never did the table examples. So when you're given a table of values, you're basically just giving a finite number of points. You're not giving a whole function. So let's say we're giving a table of values for position. So you don't have the whole position function. I'm not going to graph them exactly, but you know at time 0, position's 5, and then it's 3, and then 7, 8, 5, 7, 2, 4, 9. So you're just given some points. And basically, all you can do is use the slope formula here at this point. They can ask you to find the average velocity on the interval from 0 to 8. Because average velocity is just the change in position over change in time, right? So it's the difference in position, so it's position at 8 minus position at 0 over 8 minus 0, the difference in time. And so you can read those values off. So we have 9 minus 5 over 8, that would equal 1/2. So the average velocity over the interval is a half. That would be the slope of the secant line. That'd be the slope of the line connecting the first point, 0, 5, to the last point. So you're not finding the slope at any one point. You're finding the average slope. The other thing they can ask is for you to approximate the velocity at a particular value. And for that, if they ask us to approximate the slope of this position graph, the velocity is the SCT, it's the derivative of the position, you would have to know the slope of the tangent, and you can't do that. You can't find the slope of the tangent here. You only have, you have the point there, but that's it. So what you do is you use the slope formula. You use 2 points nearby. So if I'm interested in finding the slope, this position graph at 3, 8, I'll just use that point and the one before it, that point and the one after, or the one before and the one after. Those are like the only, because you're trying to get the slope as close as you can to when t equals 3. So we really want the velocity at time 3, but we're going to approximate it by taking the change in position over change in time. And since I want to approximate the velocity at time 3, either I want to be as close to time 3 as possible. So my possible choices, I could use change of position over change in time with the point 2, 7 and 3, 8. And in that case, my approximation would be position of 3 would be 8 minus position 2 would be 7 over 3 minus 2. And that would give us 1. So 1 would be a good approximation for the velocity at 3. Another possibility would be to use the point 3, 8 and 4, 5. So I could approximate the velocity at 3 by taking a change in position. So I'd have 8 minus 5 over change in time, 3 minus 4. So I'd have 3 over negative 1, which is negative 3. And then the other possibility, some people like to use, if they ask you for the derivative at a particular value and it's there in the table, some people like to use the point before along with the point after. So if we use these 2 points, we get an approximation of position at 4 would be 5, minus the position at 2 would be 7, over 4 minus 2, and I get an approximation negative 2 over 2, so that equals negative 1. Your approximation. But what you would not want to do if you're trying to approximate the slope of the tangent of 3 is use 2 points that are not right by 3. If you use 7 and 8, you wouldn't get it right. Okay. The other type of table problem we could have is if you're given a table for velocity values. So basically, again, you're just given some points on the velocity graph. They can still ask you how to find the average acceleration over the interval. That you can definitely find, as long as you have the values of the velocity at 0 and 10, and you do. So remember, average acceleration is delta v over delta t. So it would be v of 10 minus v of 0 over 10 minus 0. V of 10 is 9. V of 0 is 6. 10, so we would get 3/10. And that would be the average acceleration. So it would be the slope of the secant line to the graph, the velocity graph. They can ask you to approximate the instantaneous acceleration, again, by using the slope formula. If they want us to approximate the acceleration at time 5, I can't get dv dt, which is the acceleration, so I'm going to set it for delta v over delta t. It's approximately equal to. Now, again, you can choose. If it's at 5, I can use 4 and 5, 5 and 6, or 4 and 6. As long as I'm, right around the 5. So I could use 4 and 5, 5 and 6, or I want to use 4 and 6. I have those 3 choices. I'm just going to do one of them. Let's say you want to use 4 and 6. So I could take the change in velocity. So v of 6 minus v of 4 over 6 minus 4. So we'd have, v of 6 is negative 4 minus 0 over 6 minus 4 is 2. And it would be approximately equal to negative 2. That would be an acceptable approximation. Okay, but you'd have to use points either there at 5 or before and after, but not far away. Okay, so those were the last 2 problems or examples from day 24. Let's move back to day 27 where we are today. Okay. So what I asked them to do today was to find the velocity given the position function, make a sign chart for the velocity. So you have to know how to go from position to velocity. Velocity is the derivative of position. Now t cubed over 3, let me write that here, t cubed over 3. When you're rewriting this, as a number, a coefficient times t to an exponent, the number should not change. The only thing is you don't see a number in the numerator. If you don't see a number that's multiplied, oops, I just dropped the pen. That number is a 1. So t cubed over 3 is the same as 1/3 t cubed. Right, so when we take the derivative of 1/3 t cubed, 3 times 1/3 is 1. So we get 1t squared. Take the derivative of minus 3t squared. We have minus 6t. And the derivative of the 8t is plus 8. There's our velocity function. That'll tell us the velocity at any time. Now, if you want to make a sign chart for a function, first find out where that function is 0. Because any function can change sign when it's 0 or when it's undefined. So you set it equal to 0, and to solve that, you're going to want to factor. And so the values that make it the velocity 0 are 2 and 4. The velocity is defined everywhere. There's no value of t. If I plugged it in, I'd be dividing by 0. So the only time the velocity could change sign would be at 2 and 4. So we start all our motion problems at t equals 0. But the only numbers where it could change sign are 2 and 4. So I only put those numbers on. So now we take test values. You pick a time between 0 and 2, like 1. No matter what time you pick between 0 and 2, if you plug that time into your velocity, you're going to get the same sign. Now I'm just choosing 1 because it's easy to work with. When you plug 1 into the velocity to figure out if it's positive or negative, plug it into the factored form. It's easier. So if t is 1, t minus 2 would be negative, and t minus 4 would also be negative, because 1 minus 2 is negative, 1 minus 4 is negative, the product would be positive. So no matter what time you pick between 0 and 2, you plug that into the velocity is positive. So the velocity is positive for all times between 0 and 2. You do the same thing. You pick a time between 2 and 4 to determine if the velocity is positive or negative. Take a number like 3. T minus 2 would be positive, but t minus 4 would be negative. So the product would be negative. And finally, you take a value, so I plugged 3 into the velocity. You take a number greater than 4, such as 5. Both factors of the velocity would be positive, so the product would be positive. Now we know we have a sign chart for velocity. We know for what times the velocity is positive, when the object's moving right, what times the velocity is negative, so we know when the object's moving left. And also we know when the velocity changes sign. We know when it turns around. It would turn around at 2 and 4. Okay, the second part of this, we're asked to make a sign chart for the acceleration. So we'll find the acceleration, which is the derivative of velocity. So if we take the derivative of our velocity function, we get 2t minus 6. So we found our acceleration. Now we want to make a sign chart for acceleration. We want to know for what values of t acceleration is positive and for what values of t it's negative. So before we can put any other numbers other than 0 on here, we have to find out when acceleration is 0 or undefined. Again, it's always defined. We just got to find out when it's 0. And if you solve this, acceleration equals 0 when t equals 3. So the only time the acceleration could change sign would be at 3. So for any time between 0 and 3, if I plug in a time, I'm going to get the same sign. I'll plug in 2. Now, you're trying to find the sign of the acceleration, so make sure you're plugging the 2 into the acceleration, not velocity. At 2, the acceleration 2 times 2 minus 6 is negative. So for any value of t between 0 and 3, acceleration will be negative. And then you take a value of t greater than 3, such as 5. 2 times 5 minus 6 is positive. It doesn't matter what value of t I picked that was greater than 3, I would have got a positive value for acceleration. Now I know an acceleration is negative, which is when the velocity is decreasing. That's why its slope, acceleration, is negative. And we also know when the acceleration is positive, which is when the velocity is increasing, because its derivative is positive. So if all I asked you was when does the velocity, I didn't ask it, but I wish I did. If I said when is the velocity increasing, any function is increasing when its slope is positive, so when acceleration is positive. I could have used just the sign chart for acceleration. So you'd have to know that means its derivative, acceleration, is positive. And it's positive from 3 to infinity. So my answer would have been from 3 to infinity. The reason I just threw that in there is because the real question I asked is when will the object speed up? Speed increasing is not the same as velocity increasing. When you're looking for when an object speeds up, when the speed is increasing, you have to find out when velocity and acceleration have the same sign. So you want to look at the sign charts for velocity and acceleration together and find those intervals where they're either both positive or both negative. Now, I'm just going to copy my sign chart for velocity right above it so we can see. Our velocity sign chart, let me just take a look back here. Okay, when positive, negative, positive, 2 and 4. So they both start at 0. Line them up, you know, it makes it easier. So 2 would be about here. and 4 would be somewhere over here. This one went positive, negative, positive. So the object will speed up when they have the same sign. So between 2 and 3, they would both be negative. For any time between 2 and 3, they're both negative. So it's going to speed up just in the negative direction. It's going to speed up to the left. And also for times greater than 4, they'll both be positive. It'll speed up to the right. So 4 to infinity. And when will it slow down? That's when the velocity and acceleration have the opposite signs. Well, I don't have to worry about, at 2 and 4, the velocity is 0. So I don't have to worry about that. And at 3, acceleration is 0. But if I really wanted to be really picky, I would check out the 0. But let's take a look. So we see velocity, acceleration have different signs from 0 to 2. So I definitely want to go from 0 to 2. Now at 0, if you plug 0 into your velocity function, I got to look back at that. You're going to get positive 8. I just want to see if I need a bracket or a parenthesis. It's not a big deal. So the velocity of 0 is positive 8. And if you plug the 0 into your acceleration, the acceleration of 0 is negative 6. So they do have opposite signs of 0. So technically, I guess I should include that. So it's slowing down when they have opposite signs, so from 0 to 2, and also from 3 to 4. I don't have to worry about those endpoints. None of them 0. Not the opposite. Okay. So that was our little fun there. Now we want to go over review 1 for the test. Now, on the test, you got to know your basic concepts, okay? And that's the most important thing, and that's what's in the first column of the big chart that I gave you. Because you're going to be given information about one of these motion functions, but in the form of a graph, an equation, or a table. The concepts are the same. It's just you have to know how to interpret what you're given. So in the first part of our review 1, you're given the equation for the position function. First thing they ask you is the velocity. Well, velocity you have to know. They don't say average in front. They're talking about instantaneous. It's the derivative of the position function. So v of t is equal to negative 8t plus 16. This here is just reminding us that for all motion problems, time is greater than or equal to 0. Right, that's our answer for the first problem. When does the object change direction? You have to know an object changes direction when velocity changes sign. Velocity changes sign. So the only way you're going to find out when v of t changes sign is to make a sign chart for velocity. And to make a sign chart, you have to find out first when the velocity is 0. If you set the velocity equal to 0, that happens when t is 2. So for your velocity sign chart, when you start at 0, the only place the velocity could change sign, the only time it could change sign would be at 2. You mark it off at 2. You take a value of time between 0 and 2, such as 1. If you plug that into your velocity, you get a positive. Negative 8 times 1 plus 16 is positive. And the value greater than 2, you're going to get a negative. Okay. Then you look at it. Does the velocity ever change sign? Yes, at t equals 2. So that would be when it changes direction. Remember, when velocity is positive, it's traveling to the right or up. When velocity is negative, it's traveling left. So if it's traveling right, then left, it turned around at 2. What's the total displacement? When you're asked for total displacement, you have to know that all that is final position minus starting position. You don't divide by anything. It's just where it is, its position at time 5 minus its position at time 0. When you plug 5 into your position, negative 4 times 5 squared, that would be negative 100, plus 16 times 5 plus 80, that would be negative 20, plus 1 would be negative 19. So you would get negative 19 minus position at time 0 would just be 1. Negative 19 minus 1 is negative 20. So displacement can be negative. Well, that's telling you that from the beginning to the end, it's 20 units to the left of where it started. That's all. So displacement is negative 20. What's the average velocity? Average velocity is change in position over change in time. So it's the difference in position, so the position at time 5 minus the position at time 0 over the difference in time, 5 minus 0. The position at 5, well, that's the one we just calculated. Oh, we did this position of 5 minus position. That's just the displacement, the numerator. Remember, that came out to be negative 20. We just did that. The displacement is position of 5 minus position at 0. Over 5 equals negative 4. So the average velocity would be negative 4. Total distance. Total distance is not always the same as displacement. If your object turns around, they're not going to be the same. Distance traveled, in order to find the total distance traveled, you need to know its position at the following times. The start time, which is time 0, finish time at 5, and you have to know where it is whenever it turns around. This object's moving back and forth in a number line. So you got to know where it is on the number line when it turns around. And we just figured that out before. We found out that it turned around when t was equal to 2. Now, we're going to plug each of these into the position formula. S of 0 is 1. If you plug 2 into the position function, you get 17, I believe. And when we plug 5 in, that was negative 19. We had done that earlier. So you have this object, it's on a number line. Think of a number line. At time 0, it's at 1. So it starts out at 1, time 0. At time 2, when t equals 2, it's moved over to 17 on the number line. So 2 seconds later, it has traveled from 1 to 17. So it's already traveled a distance of 16. And then between times 2 and 5, it travels back, it turns around. Remember we said it turned around? And it goes all the way back to a position of negative 19. So when it goes from 1 to 17, from time 0 to time 2, to figure out how far it travels, take the absolute value of the difference. So going from 1 to 17, you subtract and take the absolute value. It's going a total distance of 16. Going from 17 back to negative 19, subtract. It doesn't matter the order you subtract, which one goes first. It's going to take the absolute value. You're going to get 36. So it travels 16 units to the right and 36 units to the left. So altogether, it travels a total of, if we add them, 52. So that's how you get the total distance. You have to find out its position, beginning, end, and when it turns around. Now, if an object's moving back and forth, left and right on a number line, it's farthest left at one of these times, either at the beginning, at the end, or when it turns around. So just look at your number line. Which one of those positions is farthest left on the number line? And if you look at them, the negative 19 is the position that's farthest left. So it's farthest left because it says when, you got to get the time, at t equals 5. When is it farthest right? It's going to be farthest right at one of these. And if you look at those positions, the position that's farthest right on the number line is 17. And that's the position of time 2. Okay, question 7. When's it moving left? You got to know it's moving left when velocity is negative. So you want to look at the velocity sign chart. Remember, we found out when velocity was 0, we made a sign chart. And you can see the velocity is negative from 2 to infinity. So you want to write from 2 to infinity. Let me just make sure I'm recording. That would be bad. Okay, I am. Back to it. Okay, next page. Find acceleration. Okay, again, they didn't say average, so you got to use derivatives, right? Acceleration is the change in velocity over change in time. dv dt. Not using the deltas. If they said average acceleration, I would do delta v over delta t. Acceleration. So we have to take the derivative of the velocity. Now the velocity was negative 8t plus 16. When you take the derivative of negative 18 plus 16, you just get negative 8. So a of t is just always negative 8. It doesn't change. So I could, when you find a new function, velocity acceleration, it's nice to make a sign chart. But what's weird about this one, they start out at 0. You're supposed to mark it off when it could change sign. Well, negative 8 is never going to be 0. Never undefined. It's always negative. There's no other numbers you should put on this sign chart. It's just negative for all values of t. So the next question says, when is velocity increasing? Any function increases when its derivative is positive. The derivative of velocity is acceleration. So I have to interpret this as them saying, well, velocity is increasing, going up, when its slope, when its derivative is positive. If I look at the sign chart for acceleration, I see it's always negative. It's never positive. So you could write never. Or you can write an empty set. There are no values. If they said, when is velocity decreasing, that would be always. I could say from 0 to infinity, because it's always decreasing because its derivative is always negative. Now comes the question, when is speed increasing? Speed increases when velocity and acceleration have the same sign. So you want to line up the velocity sign chart with the sign chart for acceleration that I have up there. Now the velocity sign chart we made somewhere, come back to see it, okay, it changed to 2 and it went from positive to negative. So I'm starting at 0, 2 over here, it's positive, negative. So when is speed increasing? They have to have the same sign. So you see, for times greater than 2, they're both negative. So it's going to speed up when t is greater than 2, or we can write from 2 to infinity. But again, you got to know the concept. Speed increases when velocity and acceleration have the same sign. They're both positive or both negative. This time we're given an equation for velocity. Okay, so first thing they ask, when is the object moving right? Okay, the core concept here is a velocity is moving right when an object is moving right. I think I just said velocity is moving right. I'm sorry, guys. Still tired. It's after school. An object is moving right when the velocity is positive. They gave you the velocity function. You want to know when it's positive. let's make a sign chart for velocity. That's a great way to know when any function is positive or negative. Make a sign chart. And to make a sign chart, you first want to find out when it's 0, so you know where I could change signs. So if we set this equal to 0, we could solve it by factoring. First I would factor out the 5. So our velocity is 5 times t minus 2 times t minus 4. So our velocity would equal 0 when any of the factors is 0. Now 5 is never going to be 0, so don't write that down. So the product will be 0 when t minus 2 is 0, or t equals 2. Or when this factor is 0, that could be 0 if t was equal to 4. So those are the only times my velocity could change sign. So when I make my velocity sign chart, again, we're going to start at 0. It can only change sign at 2 and 4. Only put those numbers on it and take test values. You take a number between 0 and 2, such as 1, and look at the sign of the t. 5 is always positive. T minus 1 would be negative. T minus 4 would be negative. Negative times negative times a positive. It's still going to be positive. You take a number between 2 and 4, such as 3. Plug it in for t. Positive, positive, negative. The product is negative. Then you take a number a time greater than 4, like 5. The factors are positive, positive, positive. The product is positive. Now we can answer we can answer 11 and 12. When is an object moving right? That's when velocity is positive. We know from 0 to 2 and from 4 to infinity. I know at 2 the velocity is 0. It's not positive there. And I know at 4 the velocity is 0. It's not positive there. At 0, though, if I wanted to be real careful, I could plug that in, and I see the velocity is 40 when t is 0. So I would include the 0. So it's moving right from 0 to 2, and then from 4 to infinity. When does it turn around? Well, that's when the velocity changes sign. And that occurs at 2 and at t equals 4. So t equals 2 and t equals 4. You just put a comma between. 2 different times it turns around. Average acceleration. Average acceleration, we're always going to use the deltas, right? You have to know acceleration, that's change in velocity over change in time. So it's v of 10 minus v of 0 over 10 minus 0. Oh, v of 10. Okay, I think I remember these numbers. You plug 10 in there, you get 240 minus v of 0, that's 40 over 10. 200 over 10 is 20. So the average acceleration would be 20. And we're not talking about units here. We're going to get into that soon. Find the acceleration. They're not saying average. They mean instantaneous. So that's not delta v over delta t. That's dv dt. It's the derivative of velocity. Oh, I just kind of moved that away. So the derivative of a velocity function would be 10t minus 30. So a of t equals 10t minus 30. That's our acceleration. Moving on. Okay, we know, let me just write that down. So the acceleration we said was equal to 10t minus 30. So at time 2, would be 10 times 2 minus 30. That's negative 10. What? Oh, when is the velocity decreasing? Any function is decreasing when its derivative is negative, right? Any function is decreasing if its slope is negative. So the derivative of velocity is acceleration. So it's decreasing when acceleration is negative. If you want to know where anything is positive or negative, look at its sign chart. To make a sign chart for acceleration, first find out if there are any times when acceleration could change sign. Was it ever equal 0? Or is it ever undefined? Well, acceleration would equal 0 when t equals 3. So the only time it could change sign is at 3. It's always defined. You look at times between 0 and 3, plug them into acceleration, like 1. Acceleration at time 1 would be negative. 10 times 1 minus 30 is negative. If you take a time greater than 3, like 5, it doesn't matter which one you pick. You're going to get the same sign. That's the beauty of this. 10 times 5 minus 30 is 20, so that's positive. We said velocity is decreasing when acceleration is negative. So from 0 to 3. Now, I know it's 0 at 3. I don't have to worry about that one. At 0, the acceleration at the 0 would be 10 times 0 minus 30. So it is negative. So I guess I'll include that. So from 0 to 3. And we're just finding out where acceleration is negative. 17. When is speed decreasing? Speed is decreasing when velocity and acceleration have the opposite signs. So again, we want to line it up with our velocity sign chart. Got to look back at that one. We try to line them up. It makes it easier. Back. Oh, here we go. Our velocity sign chart. Is this the same one? Oh, goodness, this is the same one. I think it might be different. Oh, nope. Still. Okay, it would change sign at 2 and 4. Positive, negative, positive. So I'm going to put the 2, I'm going to put it about here so it'll line up, and then a 4. And it went positive, negative, positive. Okay, so we're looking where speed is decreasing, where it's slowing down, for where they have opposite signs. I hear cheering outside. I think our field hockey team is doing well. All right, so from 0 to 2, they have opposite signs. Not 2 to 3, they have the same sign. And 3 to 4, they would have opposite signs. So 0 to 2, I guess I better check out at 0, because again, you know, I know velocity is 0 here and here. They couldn't have opposite signs. But at 0, we have 0. I got to go back look at the velocity. At 0, it'd be positive 40. So they do have opposite signs at 0. Because A of 0 is negative 30 and B of 0 is positive 40. So they have opposite signs from 0 to 2. I'll include the 0. And also they have opposite signs between 3 and 4. Okay. Now we're given a graph of position. So important. When you're looking at a graph, it's so tempting just to ignore what it's called and just look at what it's doing. You got to always, before you answer the question, relate it back to the function whose graph you're given. So you're given a graph of the position. Anytime they ask me a question, I'm going to state what I know is true about that, and then I'm going to relate it back to position. Well, the first one I don't have to really do that, because it's just what is displacement. Displacement is always final position minus starting position. You can read the graph. This is a graph of position. S of 10 is 3. And the position at time 0, you just read the graph, is 0. So we get 3 minus 0 equals 3. That's the displacement. Average velocity, average, remember we're going to use the deltas, is change in position over change in time. Right? Velocity is ds dt, it's the derivative of position. Average velocity is delta s over delta t. So we need to take the position at 10 minus the position at 0. That's just the displacement. We already know that's 3. And put it over the change in time. So we're going to get 3/10. that is would be the slope of the secant joining this first point to the last point here. When is the object moving left? So first write down your basic truth. An object's moving left when the velocity is negative. Now relate that back to what you're looking at. You're looking at position. Velocity is the derivative of position. So you want to know where the derivative is negative, and the derivative is the slope. The derivative of s is the slope of the graph of s of t. So you're really looking, where is the slope of the position graph negative? So the slope would be negative wherever it's decreasing, so from time 2 to time 6. Oh, that's not the only time. So from 2 to 6, and then again from time 9 to 10. So from 9 to 10. I'm not worried about the endpoints. Technically at 10, I guess we could include that. Should I worry about that? 2. Yeah, 2 with the slope is 0. And at 6 it doesn't even exist. So we're just looking where the velocity, which is the derivative of position, is negative. All right, when does the object turn around? So first write down the base, what you know is true. An object turns around when velocity changes sign. Then relate it to what you have. Velocity is the derivative or slope of position. So you're looking for when the velocity is the derivative of position. And another word for derivative is just slope. So you're looking for where the slope of the graph of s of t changes sign. In other words, where does the slope go from positive to negative or negative to positive? So if you look at your graph, the slope is positive, it's increasing the function, and then it decreases. So at time 2, the slope changes from positive to negative. You know, if you want to, you can make a little sign chart for the slope to the velocity right underneath it. Yeah, why don't we do that? So the velocity, the slope is positive from 0 to 2, and it's negative from 2 to 6, positive from 6 to 9, and negative from 9 to 10. All right, so we said we're looking for where, we're looking when it changes sign, the velocity. So it changes sign at 2, 6, and 9. So at t equals 2, t equals 6, and t equals 9. That's when it turns around. When is velocity positive? That's when the slope of position is positive. And we just did that. So we'll just, so the slope is positive from 0 to 2. You can include the 0 or not, I don't care. So from 0 to 2, actually it's 0, so not there, it doesn't exist. From 6 to 9. And that's it. When is acceleration positive? That's, again, related to what you have. That's when the second derivative of position is positive. Second derivative is positive when the graph is concave up. So you're looking where the graph of s of t is concave up. And if you look at your graph, it's concave up from t equals 4 to t equals 6. Okay? So from 4 to 6. Is the acceleration positive or negative? Again, related to what you're given. You're getting the graph of position. Acceleration is the second derivative of position. If you want to see if the second derivative is positive or negative, look at the concavity. So let's look at the graph at time 3. At time 3, if you look at this graph right here, it's concave down. So the second derivative is negative. because the position graph is concave down there. Is v of t positive or negative related to what you have? Velocity is the first derivative of position, so it's the slope of s of t at t equals 3. So look at the graph. At 3, is the slope positive or negative? That's negative because it's decreasing. So it also be negative. What is v of 7? Okay, related back to position because that's what you're looking at. It's the first derivative, which is the slope. So we want to know is the slope of s of t at t equals 7. Oh, we want to know what it is. What is it? Okay. Let's go back and look. At t equals 7, we're trying to figure out the slope. Now, we can actually figure it out because the slope at any point on a straight line is always going to be the same. So if you figure out the slope for this whole part of the graph, its whole line, it's the slope at every single point. And slope is change of y's over change in x's. In general, right? So 4 minus negative 2. 4 minus negative 2 over 9 minus 6. So 6 over 3 is equal to 2. So the slope at every single point on this line is equal to 2. Okay, so we'll figure that's 2. But we use the slope formula to get it. Next, we have what is the velocity at 2? Related back to position because that's what we're looking at. So it's the derivative of position at 2. First derivative is always just the slope. So we want the slope of s of t at t equals 2. We look back at our graph of position. Find the point where t equals 2. All right, it's right here. The slope, it's supposed to be there. The slope there is 0, right? Oh, I'm not really lined up. So it's just 0. 28, distance traveled. Distance traveled, you know, you always have to know its position. You have to know the position at the start time, at the finish time, at the turnaround time. Now remember, we already found those in an earlier question. Let me just go back. We got 2, 6, and 9. Remember that was when the velocity changed sign? 6, 9. So I'm going to have to know its position, not only at time 0, but at 2, 6, and 9. Now to find these positions, I just got to read the graph. So, let me see if I have a copy of this, so I don't have to keep flipping back and forth. Okay, so if you look at your graph at time 0, okay. At time 0, position is 0. At 2, because it's a 0.22, the position is 2. 6, there's a 0.6, negative 2. So it's negative 2, 9, 4, 10. Oh, it got kind of cut off on yours. It's supposed to be a 3. So to get total distance, you got to take the absolute value of the consecutive differences. It goes from 0 to 2 on the number line, so it travels 2 to the right. Then it goes from 2 to negative 2. 2 minus negative 2, that would be 4. It travels 4 left. Goes from negative 2 to 4. Negative 2 minus 4 would be negative 6. We take the absolute value, so 6. Travels 6 to the right. And then going from 4 to 3, take the absolute value of the difference, you get 1. When you add up all these little distances, left and right, you're going to get 13. Righty. Okay, next one. We're given a graph of the velocity. Oops. When does the object move left? First write down the basic truth. An object moves left when the velocity is negative. you're looking at a graph of the velocity. I don't have to change to derivatives of something. When you want to know, when you have a graph of a function, you want to know where it's negative, just look when it's below the x-axis. So the values, the y-coordinates on this graph are negative from 0 to 1. And technically, I guess I should include the 0, not the 1. At 1, the velocity is 0. That's not negative. When does the object change direction? The basic truth that an object changes direction when the velocity changes sign. You're looking at a graph of the velocity. When does it change sign? That's when it crosses the x-axis, or the t-axis. Now you can see at t equals 1, it goes from negative to positive. So it's traveling left and it's traveling right. It's changing direction. So at t equals 1. When is acceleration positive? Okay, so that's not what we have. So it's related to what we have. We've got velocity. We have to know that acceleration is the first derivative, d prime, of t. And the first derivative is the same thing as saying the slope. So when is the slope of v of t positive? That's when it's increasing. The slope will be positive. So the slope is positive from 0 to 2 and 5 to 7. Let's see, one second. I guess we could include the 0. The derivative, well, doesn't exist at 2, doesn't exist at 5. If you want to include the 0, include the 0. When is the object at its greatest speed? Well, speed is the absolute value of the velocity. So if you wanted to graph the speed function, it would be the same where the velocity is positive, the absolute value of positive is positive. But wherever it's negative, you would multiply it by negative 1 to make it positive. So it would just be up here. Right? So this would be the speed graph. When is the speed the greatest? Well, the greatest speed is 3, but it actually happens twice. In my answer key, I think I only wrote one of them. It should be at t equals 0, that's 3. The speed is, so at t equals 0, the velocity is negative 3. So the speed is positive 3. And it's also 3 when t equals 2. So really at t equals 0 and t equals 2. That's when the speed's going to be 3. Okay, next one. Sorry, I'm rushing. I have to finish this. Okay, what is the average acceleration? Use those deltas. Average acceleration is change of velocity over change in time. So we're going to take the velocity at time 7 minus the velocity at time 0 and put it over the change in time. Velocity at time 7, if we read the graph, equals 2. And so where is that here? So it's 2 minus velocity at time 0 is negative 3. Over 7. So it looks like we get 5/7. Which is just the slope of the secant line drawn to the velocity graph from 0 to 7. Wow, they're cheering. I think our team is doing well. Okay, what is acceleration at time 3? You're given velocity graph related back to velocity. Acceleration is the first derivative of velocity. And the first derivative is the same as the slope. So it's the slope of v of t at t equals 3. Let's look at our graph and look at the slope there. At 3, where are we? We're right here. The slope, because it's a straight line, is the same as the slope of the whole segment. The slope at any point on this segment is the same as the slope of this segment. So we'll just use slope formula. We got this point here. Wow, good stuff's happening. So to find the slope, we take change of y. So we can do 3 minus 0 over change of x's, even though they're not x's, they're change. 2 minus 5. So 3 over negative 3 is negative 1. So the slope everywhere along this line is -1. So the slope here at 3 is going to be -1. When is the object speeding up? Okay, for that, we need to compare the sign charts of velocity and acceleration. Let's make a sign chart. We have to see when they have the same sign. So for the velocity, trying to find a graph. I'm just going to do a rough sketch of functions so I don't have to go back. So this is the velocity. 7, 5, 1, 2. Okay, so here's the velocity. I can make a sign chart for velocity. I just got to look at where it's positive and where it's negative. So from 0 to 1, if you look at your graph of velocity, you see it's negative. From 1 to 5, it's positive. At 5, the velocity is 0. And then from 5 to 7, the velocity is above the x-axis, right? The axis, it's positive. The graph stops at 7. So that's our velocity sign chart. Acceleration is the slope of the velocity. So if you look at the slope is positive from 0 to 2. It's going up, it's increasing. So from 0 to 2, our slope is positive. From 2 to 5, my velocity is decreasing, its slope is negative. And from 5 to 7, it's increasing, its slope is positive. So they're asking where it's speeding up. So it's going to be speeding up from 1 to 2, and then from, this thing stops at 7. So from 5 to 7, they have the same sign. 1 to 2, and then from 5 to 7. They're both positive. Yeah, so it only sped up in the positive direction. There was never a time where it was both the velocity was negative and its slope was negative. That didn't happen. Never sped up in the negative direction. All right, up to tables. Tables, you're going to be using slope formula. Average velocity, change in position over change in time. So S of 10 minus S of 0 over 10 minus 0. They have to actually give you these values or you couldn't do this. Just make sure the change of positions in the numerator. So S of 10 is 6 minus S of 0 is 5 over 10. We get 1/10. Approximate V of 9. Well, time 9 would be in here, right? So you can the only points would make sense would be these 2 points. So we're going to approximate V of 9 with the change in, instead of ds dt, we're going to take position at time 10 minus the position at time 8 over 10 minus 8. We're approximating it with a delta S over delta t. So we have 6 minus 8 over 10 minus 8. Negative 2 over positive 2 is negative 1. So it's approximately equal to negative 1. We don't know what it equals. Okay, let's choose. Table for velocity. Average acceleration, delta V over delta T. So it's going to equal V of 12 minus V of 0 over 12 minus 0. V of 12 is negative 3. V of 0 is 1 over 12. Negative 4 over 12 equals negative 1/3. Approximate the acceleration at time 1. Well, 1's right here. It happens to land right on point. So you can use the 0, the 1, the 1, the 5, or the 0 and the 5. It's up to you. As long as you use one of those 3 combos. So the 0 and the 1, The 1 and the 5, or the 0 and the 5? Let's go the 0 and the 1 this time. So we're going to take v of 1 minus v of 0 over 1 minus 0. V of 1 is negative 2. V of 0 is 1 over 1. So v is approximately equal to negative 3. Acceleration of time 1 is approximately equal to negative 3. As long as you show what points you're using and those points are there or nearby, you're good. All right, gotta go. It was a pleasure. I hope you rewind this and do this instead of trick-or-treating because it's better for you and doesn't rot your teeth. Where is my little thing? All right. See ya.